Welcome to The Explainer. Today, we are diving deep, literally, into the incredibly complex geometry hidden thousands of feet right beneath our shoes. You see, when the energy industry shifted from vertical to horizontal drilling back in the 1980s, it wasn't just, a simple upgrade in machinery. It actually required a total, ground-up reinvention of the mathematics used to predict how fluids flow underground. So let's explore the math of the deep.
Here's our quick roadmap for today. We're going to kick things off with the horizontal revolution, then dig into underground permeability. From there, we'll unpack the two heavy-hitting math models, steady state and pseudo-steady state. Then we'll adapt those for gas and two-phase flow, and wrap it all up with a look at the multilateral future.
All right, part one, the horizontal revolution. Why did engineers completely tear up the playbook and change how they drill?
Imagine a standard vertical well. It essentially just punches straight down, meaning it only touches the target reservoir for the exact, limited thickness of that specific rock layer. If you're dealing with a really thin reservoir, say less than 50 feet, or if the rock is just super tight and stubborn, a vertical well barely even scratches the surface of the resource. The flow is strictly radial, pulling inward like a circle toward a straw. But horizontal wells, they completely flip the script. By turning sideways, they drastically extend the contact area, morphing that basic circular drainage into this wild, complex mix of radial, linear, and elliptical flows. It's a total game changer.
Moving right along to part two, underground permeability. Because, spoiler alert, the Earth is not just a perfectly uniform sponge.
So, let's talk about permeability anisotropy. I know, it sounds like a massive mouthful, right? But honestly, you can just picture it like the grain in a piece of wood. Anyone who's chopped firewood knows it splits way easier along the grain than against it. Well, deep underground, fluids act the exact same way. They flow much more easily in specific directions, totally dictated by the immense horizontal stresses of the Earth itself. If engineers ignore this natural grain, they are walking right into a massive, very expensive mistake.
And if we look at the numbers from Economidas' model, the stakes become crystal clear. Orientation is absolutely everything. Let's say you have an isotropic reservoir, meaning it acts the same in all directions. You get a solid productivity index of 0.98. Awesome. But if that rock has a grain and you drill the wrong way, what engineers call an unfavorable azimuth, your productivity absolutely tanks down to 0.46. You are literally losing more than 50% of your production just by drilling in the wrong direction. But if you measure the stress first and drill perpendicular to the maximum permeability, boom, you're right back up to a 0.91 index.
So that brings us to part three, steady state, the ellipse. How on earth do engineers actually predict this flow when they're totally blind to the underground shapes?
Well, to translate a messy 3D reality into math you can actually solve, the 1988 Joshi model pulled off a brilliant hack. It essentially splits the inflow into two separate planes. If you look at it straight from above, the model treats the pressure boundaries as an ellipse, using the two ends of the well as the focal points. Then, if you look at it from the side, the cross-section, it just behaves like standard radial flow. By snapping these two flow shapes together, Joshi handed engineers a highly workable equation to predict steady-state production.
Then, building on that, we get the Furui model. Now, Furui takes a slightly different angle. Instead of an ellipse, they pictured the horizontal well sitting dead center inside a box-shaped boundary. Right up close to the wellbore, the fluid is moving in a radial circle. But as you push further out into that box, the flow stretches out and dynamically morphs into straight linear paths. By basically doing the math for the pressure drops in both of these regions separately and adding them up, engineers get an incredibly accurate picture of steady flow inside a closed box.
All right, let's shift gears to part four, pseudo-steady state, the box. This comes into play when the reservoir is trapped by impermeable rock and the pressure starts dropping everywhere all at once.
When we're talking pseudo-steady state, the Babu and Ode model is basically the gold standard. To crack the incredibly nasty 3D diffusivity equation, they came up with a really clean three-step recipe. Step 1. Define a 3D bounding box that represents the drainage area. Step 2. Calculate a specific geometry shape factor. And Step 3. Apply what's called a partial penetration skin factor.
Now, you might be wondering, what is a shape factor and why do we need it? Well, because reality is messy. Textbooks love to pretend a drainage area is this gorgeous, perfectly symmetrical cylinder. But in the real world, it's usually some lopsided asymmetrical box, and the well is almost never perfectly in the center. The shape factor is the mathematical fix for that real-world weirdness. You combine that with a skin factor, which accounts for the well not reaching all the way to the edges, and engineers can finally balance the equations and squeeze out the most oil possible from bounded rock. Let's quickly pivot to Part 5, gas and two-phase flow, because we've been talking a lot about oil, but what happens when you need to run these neat geometric models for gas? The absolute beauty of these models is how adaptable they are. For a horizontal gas well, engineers take the exact same geometric foundation we just talked about, but they swap out the oil variables for gas equivalents. You throw in the real gas law, you apply pseudopressure, and you're mostly there. But here is a wild twist. You know how gas can sometimes have a turbulent, chaotic flow, what they call non-Darcy flow? Because horizontal wells have so much surface area touching the rock, the pressure drop is way less severe than in a vertical well. And that gentle pressure drop actually masks the turbulence, making the gas flow remarkably smoother.
Okay, but what if oil and gas are flowing together at the same time? That's two-phase flow, and the permeability there gets so complex that simple equations basically fall apart. So, engineers do a clever workaround. First, they calculate the absolute maximum flow potential as if it were just the standard, single-phase oil well. Then, they gracefully apply Vogel's equation to adjust the numbers, making up for the fact that gas bubbles are actively separating out of the oil. It's a really elegant mathematical bridge connecting single-phase geometry to two-phase reality.
Finally, let's look at Part 6, the multilateral future. This is where horizontal drilling goes next level. Now, common sense might tell you, hey, if a long horizontal well makes more money, why not just drill one infinitely long pipe? Well, the enemy there is friction. If a single pipe goes too far, the friction of the fluid scraping the sides literally chokes off the production rate. The fix? Multilateral wells. These are the heavy hitters used in the absolute toughest environments on Earth, recovering dense heavy oil, tapping tight coal seams, draining low permeability shales, and operating on offshore platforms where you just don't have the surface space to drill 100 individual wells.
Basically, a multilateral well is a system where two or more horizontal branches all feed back into one main vertical pipe, the mother bore. Think of it exactly like the massive root system of an ancient tree. Instead of one impossibly long pipe fighting friction the whole way, you build out a sprawling network of shorter branches, draining different pockets of the reservoir all at once. This kind of super complex architecture is absolutely vital in places like Venezuela's Orinoco Belt, where getting that sludgy, heavy oil to move requires maximum rock contact without losing all your pressure to friction.
But of course, solving one problem creates another. This setup introduces a formidable new mathematical headache. Because all those different branches are dumping fluid into one main mother bore, the pressures at those massive underground junctions have to be perfectly balanced. If one branch comes in too hot, with higher pressure, it'll literally choke out the weaker branch, or worse, push fluid backward into it. So, I want to leave you with this to chew on. As we go after tighter, deeper, and far more stubborn rock formations demanding wildly complex geometry, how is the next generation of engineers going to balance the delicate pressures of these massive, multi-branched underground networks? The mathematics of the deep, it turns out, are still far from settled. Thanks for hanging out with me for this explainer, and keep questioning the science right beneath your feet.